So, what's the number of insects when t is 0?
Isn't that just 500? Because that's the initial number.
Well, and when you plug in 0 for t, then you have e to the 0 power, which is 1. So, what's the growth rate?
2%.
Yeah. 0.02. Yeah, 2% is probably the answer they want. Graph the function using a graphing utility. You know how to do that?
Yes, I do.
What's the population after 10 days?
You just plug 10 in for t, right?
Correct.
Okay, I got 610.
Okay, I'm going to take your word for it. Does that make sense? Let's see. If it's growing at 2% per day, yeah, after 10 days, that would be approximately 20%. Would get you up to 610. So I always like doing ballpark checks to make sure that we're not off by a factor of 10 or anything. When will the insect population reach 800? How do you do that? What equation would I use?
Don't you use 800 equals 500 e to the power of 0.02 times t?
Okay, how do I solve that? In other words, I'm solving that.
I graphed it. Or I just graphed the original.
Didn't. You know how to solve that without graphing it?
No.
I think they probably want you to know how to do that.
Okay.
Almost certain of it. You've had logs, right?
Yeah.
Okay.
I had my test on it today.
This is a log problem. Whenever you have your variable in the exponent, trying to solve it, you're going to have to take the logs at some point. But we want to isolate that part of it before we take the log of both sides. So we want to divide by 500. So I get 8/5 on the left equals e to the 0.02t. Now how do I solve that using logs?
Can you take the natural log of it?
And that's the best one to use for sure because we're dealing with e. Okay. And the natural log of e is what?
Just 1, right?
Okay. And what can I do with that 0.02t now that I've taken the log of both sides?
You can just take it down to being a regular number.
Yeah. In fact, I can replace that whole thing with 0.02t because natural log of e is 1. So I've got 0.02t equals natural log of 8/5. Finally, divide both sides by 0.02. And I would almost just leave it like that.
You divide the 8/5 by 0.02?
What's that?
You divide the 8/5 by 0.02?
No, you divide this number. That's a number. You can get that out of your calculator if you look up the natural log of 1.6 and then divide it by 0.02. But whatever answer your calculator gives you is going to be approximate. It's not going to be exact. So if you want an exact answer, you got to express the answer in terms of logs. Now there are some other ways I could express that answer. Notice that the top can be expressed as the natural log of 8 minus the natural log of 5, all by 0.02. So that might be a little bit better looking answer.
Okay.
And when will the insect population double? What's the equation I'm going to use?
Just 1,000 equals 500e.
Yeah,
Or
and we're going to
102.
solve it exactly the same way.
Mm-hmm.
Instead of 8/5, we would have 2. Everything else is going to be the same. So actually, we know what our answer is. It's the natural log of 2 divided by 0.02.
Okay.
That's how long it would take to double. Is your teacher okay with you solving these graphically? Or, in other words,
Yeah, I
do
think
you
it is.
always get to use your graphing calculator on tests?
No.
Okay. But of course, yeah, you might not get to use a graphing calculator on a question like this. For
Mm-hmm.
one thing, if you express your answer in terms of logs, you don't need a calculator at all to do it. I didn't use a calculator
Mm-hmm.
when I just did it. So um, I would think that he would want you to be able to do it without graphing it. Number 2 next.
Mm-hmm.
Okay. These seem to be pretty similar. Notice that the t is not always in the same units. In question 1, the t was in days and the growth rate was 2% per day. Whereas in question 2, t is in hours, and what's the growth rate?
1%.
Per hour. You know how to graph it. What's the population after 4 hours?
I got 1,040.8.
Okay. So when you got that, is all you did was
I just plugged
plugged it in. You
4
didn't
hours.
graph it. Okay. When will the number of bacteria reach 1,700? And now I'm assuming. Let me guess how you did this. You graphed that, and then you graphed y equals 1,700 and wherever they crossed.
Mm-hmm.
Okay. And that's a perfectly good way to do it. Never used this. Oh, I like that. Except never used this drawing tablet or function before, except it's too thin. I don't seem to have the ability to increase its thickness except with this one here. Yeah, but they give you two thicknesses, that and the tiny one. Uh, okay, what next? What problem? Next page?
I think I sent you another one, didn't I?
Yes, the second page. It takes a long time for that. I assume number 5.
Mm-hmm. And I think number 7.
Okay.
I guess we could just do them all.
Okay. Yeah. Population obeys the laws of uninhibited growth. Therefore, what is the general equation going to be?
Um, for what? Is it the a sub
If
zero?
it exhibits uninhibited growth, that's continuous growth. Is what they mean.
So is that the PERT one?
Yeah, PERT. P equals, excuse me, there's the beginning. I guess it doesn't have to be, well, we'll put an A for initial. E, and it's e to the RT. Notice that that's what all of our equations were. We had some starting beginning amount, which is a sub 0, and then it was e to the rate times time.
Mm-hmm.
So tell me how I can come up with a specific equation that models this group of mosquitoes.
So there's 1,000 originally, so it'd be 1,000 e to the power of RT.
And they give you a little bit more information. If 1,000 and there are 1,800 after one day, what does that tell us the growth rate is?
What is it? It's 800 a day.
80%.
Uh-huh.
So that tells us the growth rate is 0.8. And now we have our specific equation. As long as t is in days.
Mm-hmm.
Obviously, if I make t in hours, it changes everything, but particularly r. Okay. So what's the size of the colony after 3 days?
Let me put that in my calculator.
Hold on a second. I didn't do that right. Did I? Yes, maybe. No, I didn't. Hold on a second. We can't figure out what R is.
We can't?
Not the way I did it. The way I did it, I thought you could do it that way, but I'm realizing now that you don't get the same answer. The way you really have to answer that is you have to say it grows to 1,800 in one day, right? So I've got to solve for R. And it ends up being 9/5 equals e to the R. Take natural log of both sides, and R ends up being the natural log of 9/5. What is that? It's natural log of 1.8.
I got 0.58.
Aha. The growth rate was considerably different. And the reason is that I assumed it was being compounded only once a day. So when I saw 1,000 go to 1,800, I assumed that that was a change in 800 divided by 1,000. Therefore, the growth rate seemed like it had to be 80%.
Mm-hmm.
But if you do it based on continuous compounding, you realize that it doesn't have to be 80%. That a growth rate of 58% would cause it to grow to 1,800 after a full day. So we figured out R. So now we know what our equation is. It's 0.58t. There's our equation that models the situation. And the size after 3 days, just stick in 3 for t. How long is it until there's 10,000? Let's do that one. What do I do?
Divide the 1,000 out.
In other words, let's answer. We've got our equation. There's our equation. And notice, if I test it, it's going to work. In other words, if I put in 1 for t, I guarantee you e to the 0.58 power is 1.8.
Mm-hmm.
And that's how 1,000 grow to 1,800, even though at a growth rate of 58%. So what equation do I write to figure out how long it takes to get to 10,000 mosquitoes?
You just the same one, except you replace the 1,800 with 10,000.
Yeah. What's the next step for solving that?
Then you divide it by 1,000. You divide both sides by 1,000.
So that becomes 10.
Mm-hmm.
And now
Law.
what's t going to be?
I'm not sure.
Well, here's what we have. 10 equals e to the 0.58t. How do we solve that?
You take the natural log of both sides.
And when I take the natural log of the right side, I end up with just 0.58t. So t ends up being the natural log of 10 divided by 0.58.
Mm-hmm.
That's how long it would take to get to 10,000 mosquitoes. That's why everybody hates them.
Mm-hmm.
There aren't many limiting factors. It almost is the law of uninhibited growth, as opposed to bacteria in a petri dish, which are limited by the size of the dish.
Mm-hmm.
Whereas mosquitoes, I guess they're limited by the size of the atmosphere. Number 7 follows the exponential law. It's funny, the law of uninhibited growth and the exponential law are the same. In other words, everything in nature tends to grow with continuous compounding. Nothing in nature grows where you compound it once a year. Only bank accounts, in other words, human invention, do they introduce a concept where you have annual compound growth. Everything in nature is continuous compounding, growth or decay. So, including population. So, if it doubled in an 18-month period and the current population is 10,000, what will the population be 2 years from now? All right. What's the general equation? Population is going to be what?
For 10, or for not for 10, for 7.
Number 7, In other words, this equation is always the same.
10,000.
Well, let's just start with the general. A sub 0, meaning the initial, times e to the RT.
Yeah.
Because this one's worded a little bit different. The population doubles inside over an 18-month period. Well, that means no matter what it started with, P is going to be 2A. Right?
Uh-huh.
So I can really solve it like this. And the A's divide out. And now I know that it doubled in 18 months. So if I make T 18, now I've got 2 equals e to the 18r, natural log of both sides, and I got natural log of 2 divided by 18 equals r. In other words, the key to this problem is just like number 5, and you got to figure out r first, based on the information they give you. And you have to figure it out based on this equation. You can't figure it out based on the way I did it the first time by just subtracting the two. You get a much different rate. So this is the rate of growth of this population model. And they're saying the current population is 10,000. Well, that's going to let you go back and figure out what the initial population was. And in fact, I don't need that. I got my equation. If this is my equation, and they say the current population is 10,000, I can treat that as an initial population. Times e to the natural log of 2 divided by 18 times 2. Ah, not times 2. Times what?
2 years, so
24. Yeah, in other words, I made t in months.
Oh, yeah.
When I solved for r, I used 18, which is in months. So I got to make sure that whatever I'm solving, I use the same units for t. So it would be 24. Yeah. So here's all you have to do is solve that for p, and that'll tell you what the population is going to be in 2 years. Yeah. Been a better question if they'd have said, population's 10,000, what was it 2 years ago? Then that would have been a little tricky. You wouldn't have been able to use 10,000 as your a sub 0. You'd had to use it as p and kind of work backwards. But, all right, Sam. I will let you go. We're only doing half hour tonight, right? I'll talk to you next time.
Thanks.